One of the classic physics problems you will encounter is the Pulley problem. And here we have a simplified pulley. So from the ceiling, we hang an idealized pulley. We say idealized because we're not going to worry about the rotational energy yet. We'll get to that in a later unit. But we're also assuming that there is negligible amounts of friction, so we can ignore it. Now, what makes this simple, other than those assumptions, is that we only have two masses hanging from it and a single pulley. So here we have mass A hanging on the left and mass B hanging on the right, connected by a rope or cable that wraps around the pulley. Now, looking at this diagram, you would assume that mass A is larger than mass B and therefore has more mass. While it's possible that the densities could be different and B would actually be the heavier of the two, we can just assume in a generalized sense that the mass A is the larger two. You'll see at the end of this tutorial that if you have it the other way around, where B actually has more kilograms than A, you still get the same answer if you solve it in a general sense first, which is always a good practice when approaching physics problems. As with most force problems, the first step you want to do is draw some force diagrams. Looking at block A, we see that there is only one thing in contact with it. But first I draw the weight force down. And this is going to be the weight force of the Earth acting on object A. Counteracting that will be a tension force. I don't actually know beforehand, is it equal to, greater than, or less than the weight force. So I will just draw an arrow for the time being. When we calculate numbers later, we can adjust it. But this is the tension between the rope and block A. Now we're going to do the same thing for block B. With the assumption that it's smaller and less massive, I'll draw a smaller arrow. We can always correct that later. So this is going to be the weight force of the Earth pulling down on block B. Now counteracting that is going to be a tension force. And this tension force is going to be between the rope and block B. Now that we have our two force diagrams, it's time to write out the force equation using the second law. But before we do that, we should have a discussion about direction. We know that A, if it's the more massive one, should fall down, and B would go up. So they're opposite directions if our coordinate system is outside of the system. Now imagine for a moment that you're a tiny little ant on the rope. B's forward direction is this way. A's forward direction is this way. So if our reference frame, our metric, was going along the ride on the rope, we could define our forward direction, even though the pulley changes it in this manner. So keep in mind, a pulley really just redirects the force. If it's a pulley off its system, hanging from the ceiling, we go from a positive y direction to a negative y direction. Or if it's off a table edge or something, we do a 90-degree turn. So the pulley is redirecting our force. But if we define our positive direction as the positive direction of the motion, that means that A's net force should be positive this way, B's net force should be positive in that direction. So from an outside observer, it looks like they're opposites, but from the point of view of the rope, they're in the same direction. When we write the net force, we have to keep this in mind. So F net on block A is going to be the mass of block A times the acceleration. And that's going to be equal to, here the weight force is positive because it's in the positive direction as we defined it, meaning that the tension force acts against it, and I give it a negative number. Likewise, the net force on object B is going to be the mass of B times the acceleration. Now here the positive direction, or the forward direction if you'd rather, is the tension force. And the weight force acting against that, I give a negative number. Notice that the acceleration for both of these equations has no subscript. So it's not acceleration of A and acceleration of B. This is because the whole thing accelerates as a system. As A accelerates down, B accelerates up, which from the reference frame of the rope is all in the positive direction. Take a moment to think about this. Does it make sense? If A had a higher rate of acceleration than B, our rope would stretch and snap. Now we're assuming it's an idealized rope, so it's not springy, and we don't want it to snap, so that would move together. If B for some reason had a higher acceleration than A, that means it would be catching up, and our rope would start to bunch up, which is also not the idealized case. Even though both of those situations happen in reality, we're not quite ready to deal with friction and rotational motion to worry about that yet. Now, the tension forces are both pointing in the upward direction, and they have different subscripts, so they are not third law pairs. However, the entire rope moves as one unit. These are internal forces to the rope. In essence, a tension force acts as a force transfer. Even though they are not technically third law pairs, they kind of act like it, though the directions are different. So the magnitude of this tension force is equal to the magnitude of that tension force. Otherwise, they would not cancel out, and the rope would not move in the same manner as the blocks. All this really means is we can simplify our equations a bit more. So the mass of B times the acceleration is just equal to the tension in the rope minus the weight force on B, which is the mass of B times little g. Likewise, the mass of A times the acceleration is equal to the mass of A times g minus t. So here we have two unknowns, tension and acceleration. I am going to solve for the block B equation first. So T is equal to the mass of B times A plus the mass of B times G. I can take this entire equation and plug it into the A block's equation, meaning that the mass of A times the acceleration is equal to the mass of A times G minus m sub B A minus m sub B G. Keep in mind, the minus signs here are easy to mix up, so slow down and double check your work. Some algebra is necessary at this point. Combine the like terms, as it were. So I'm going to have on the left-hand side, the mass of A plus the mass of B times the acceleration is going to be equal to, on the right-hand side, the mass of A minus the mass of B times the acceleration of gravity. Meaning that our acceleration for the whole system is going to be equal to the difference in the masses divided by the sum of the masses, all times the gravitational constant. Alright, let's take a moment to see if this makes sense. So we have kilograms on top and kilograms on bottom. So that unit cancels out, leaving us with an acceleration equal to another acceleration. Looks good so far. But let's take some limits. What if the mass of A were equal to the mass of B? They were the two same size blocks. Well, on the bottom here we would use twice the mass, but on the top they cancel out, giving us 0, meaning that the acceleration equals 0. So if these were perfectly balanced, we would not expect them to move. They would just sit there. So that checks out. What happens if A were much larger than B? Maybe this is 1,000 kilograms and this is just a feather. Well, in that case, this little bit cancels out essentially, meaning we essentially just have MA over MA, because this little bit also only adds a tiny iota, meaning that the acceleration is essentially g, because the masses of A cancel out, which makes sense. It's essentially going to be free fall if you don't attach a significant mass to it. And what happens if B were actually bigger? Then MA minus B, we'd end up with a negative sign here, which would mean our acceleration is in the opposite direction. But since we defined this as the positive direction, the opposite direction would just mean we rotate the other way. So it seems to check out. Once you have the acceleration, you can plug it back in to find the tension, in case you have a situation where you're worried that your rope might snap. So for some of you, I know you prefer numbers when visualizing these things, so let's just make up some numbers here. If the mass of A were 10 kilograms, and the mass of B was lighter at 2.0 kilograms, well then our acceleration would be 10 minus 2 all over 10 plus 2 times little g, which gives us 8/12 of a g, or 2/3 gravity. So it's accelerating slower, which if you have access to a pendulum in a lab, you can verify. Now having that, can we solve for tension? Well, if I use this equation, I don't have to do as much algebra, so that seems appealing. The tension is going to be the mass of B, which was 2, times our 2/3 of a g, plus 2 times a g. Now, you can simplify all this and find out that it is 10/3 of a gravity, which if you want to plug that in, it's about 33 newtons of force. So if you know the limit to your rope, you can safely design a pulley system. So like most force problems, you start off with some sort of situation. Your first step, draw a force diagram, and then you're going to write an equation from the net force using the force diagram. The key here was to realize that the weight force of an A was acting in the forward direction, while the weight force on B was acting in the backwards direction. So translating your force diagram to an equation, we actually did a frame of reference shift here. We went from an XY coordinate system that was outside of the pulley system to one that was moving along with the rope. That helped us simplify things. Once you get that equation written for both objects, it just becomes a long-winded algebra problem. Hopefully that clarified some of the techniques necessary for solving system problems and pulley problems.